Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we have with us Ben Tidser. Ben's a PhD candidate in the Department of Computer Science at UCLA. He's been working on the design of efficient object-oriented systems for embedded systems. He has also designed and implemented his own object-oriented language for such systems called Virgil, as well as a compiler and runtime for it. And with that, I'll pass the podium to Ben.
Thanks. So I'm going to talk a little bit about the challenge that we're facing here. So there's 6 billion microcontroller units produced every year in the world. And they're in for everything from microwaves to washing machines to analog braking systems to sensor networks. And the goal that we have at UCLA and a lot of places is to build robust and efficient software for these guys. So robust, what I mean by that is that we have language level safety. So I'm going to talk about why we really want language level safety as opposed to maybe operating system level or hardware level safety. It has to be efficient because these things are very small. And it has to run on the bare metal because often applications are mixed up with device drivers and the operating system together, and they run directly on the hardware. So here's an example of one of the devices that we care about. It's a Mica 2 sensor node. So you can see it's about the size of $0.50. It's the core of it is a ATmega 128 microcontroller, 8-bit processor. It's got 4 kilobytes of RAM and 128 kilobytes of code space. And then built around the processor, there are things for example, doing wireless communication, the CC1000 radio, and also it's got some external flash drives, external flash built into it for recording sensor data. So there's difficulties here because of the domain, foremost, the constraints, severe resource limitations. You saw there's so little memory and so little code space that you really have to be efficient no matter what you do. There's low-level hardware details, so often we have to implement device drivers for specific devices that are hooked up to the microcontroller because these are awesome and often in custom scenarios. These microcontrollers generally do not have hardware protection, which makes it difficult to implement things that sort of assume a level of safety from the operating system. Of course, there's events and interrupts and reentrancy. Programs are generally driven by the external world and not by input or by other programs. And of course, there's energy and real-time requirements because these things often run on batteries and they often have to control the physical world, such as motors. So there's requirements on the software there. And the point I'm trying to make is that existing good languages, and you can substitute whatever language you like for good, are pretty heavyweight, and especially when weighed against the sort of constraints of this domain. There's complex language services like garbage collection, dynamic compilation, class loading. These things can't be comfortably supported on these devices. And other language features such as reflection require a lot of metadata about the program for it to be processed, and that really just doesn't work in this domain. So I'm going to illustrate this with a logarithmic plot of the footprint, memory footprint, both in terms of code and data of different language implementation technologies. So on the bottom is the axis. You can see it goes from 10 bytes up to 10 to the 9th or 1 gigabyte. And sort of at the lowest level, we sort of have C and C++, these languages that are designed for writing at the lowest level. You can see that because they are so lightweight, we can get a much smaller footprint. We can get down to these microcontroller class devices. But most other language implementations just can't get past a barrier at some point, about 10 kilobytes or a couple of tens of kilobytes. And that's really bad because we'd really like to develop software in really nice languages for these things. So really the goal is to fit in this size gap, to have sort of the structures and abstractions that we have at the higher level, but be able to fit in this much smaller constrained environment. So the contributions of Virgil are threefold. I'm going to talk about most of these. The first is that at the source level, Virgil has a system of lightweight features that make it easy easier for programmers to understand where the resources are going in when they develop applications. And then the two other contributions are inside of the compiler. So there's this notion that I call the program initialization phase, whereby an application is allowed to allocate its entire heap inside the compiler. And that allows the heap to be available to the compiler to perform new optimizations. And these heap-specific optimizations, for example, can remove dead code and data. They can represent program quantities in interesting ways to compress them, and also move read-only data into the ROM, which is generally larger. Okay, so the basics of Virgil is that the overall goal is that we'd like to have strong type safety. I think the programming languages world has sort of learned that lesson over the past 20 years. So Virgil has the familiar, well-defined primitive types such as integers, booleans, and characters, and all the operations and the semantics of those types are defined in terms of themselves and not in terms of a machine. So we actually have some abstraction there. And these are, pretty much defined as they would be in Java or C#. Of course, there are bounds checked arrays of any type, so you can build an array of any type. And every access is dynamically bounds checked against the bounds of the array. And of course, compiler optimizations can remove redundant checks. There are dynamic safety checks for null and cas, but those also can be removed by the compiler through some analysis. So that guarantees that we have a mostly static type system here with some dynamic safety checks. But we'd also like to have expressive features. So not only strong type safety, but also be able to express things. So we have objects, components, and arrays, and delegates in Virgil. And I'll talk about the object model and delegates in a little bit more detail. Raw types are types for manipulating bit-level quantities. So this happens a lot on when you're writing device drivers and running directly on the hardware. You have to manipulate quantities that have various bit layouts, and that's sort of a pain when you just have integers and shift and mask. There's also support in Virgil for hardware access and writing interrupt handlers directly in the language without any unsafe code. And that's because we often have to write things that directly control devices at the register level. And so there's direct support in the source language for that. But both of these things are weighed against the need for an efficient implementation. So there's no heavyweight runtime system in Virgil at all. There's a very straightforward object implementation because the inheritance model is very simple. And then on top of that, we're going to apply some pretty sophisticated compiler optimizations to reduce resource consumption. So I'm going to talk about components real quick. Components are basically a way to encapsulate global state and behavior. Think of them as a class where all of the members are static. So what that means is instantiated only once, like a singleton, and it's accessible through its name. So on the right, there's an example piece of code. For example, it implements a timer. It's got some fields that have state that are integers. It's got some methods to start and stop it. And then it's also got a method called interrupt, which we can actually hook up to an actual hardware interrupt that can manipulate the state. So if you're familiar at all with TinyOS, it's sort of like a TinyOS component, but there's not really a developed wiring system. And I'll talk about this in a lot more detail, actually. These will serve as the unit of compile time initialization. So Virgil has a very simple class-based model. It has classes similar to Java, always pass by reference semantics, static types with dynamic safety checks. I mentioned that we dynamically check explicit downcast in the program. Single inheritance only between classes. That makes for a very straightforward and simple object model that's easy for programmers to understand how it's implemented. And there aren't any interfaces as there are in Java. And I sort of put in there, go ugly later. So I think that interfaces are probably definitely not my favorite Java language feature. And I think there are better ways to get that kind of extensibility. So that's something that I want to work on in the future. Yeah?
Generic types?
Yes, those are coming now. I'm working on that now.
Okay.
So there is no root class at the top of all inheritance hierarchies, like Java Lang object, or I think it's system.object in C#. Every class hierarchy is actually independent of each other. What this does, it reduces the size of meta objects. So a meta object has type information for a class and also has a dispatch table for a class. So for example, in Java, at least, there are 11 virtual methods in Java Lang object. What that means is that for every class that you define, you have a basic built-in cost where you need a dispatch table for those guys, even if only one class in the program overrides one of those methods. And we want to get away from sort of having this built-in cost to every single class. So that's why there is no class at the top. That also allows us to represent some objects without any object headers whatsoever. So for example, if we have a class that is not related to any other class in the program, then all of its static type information is known to the compiler, and it can represent all instances of that class without an object header, and then resolve all virtual dispatches, and then, of course, inline after that. This gives the programmer more control because they can, for example, specifically define an orphan class so that happens to be prolific. It happens to be allocated a lot to save space. They can define it as an orphan so it doesn't need an object header. This complicates code reuse because of the static types, so that's why we need parametric types, which I'll talk about at the very end. So delegates are an idea that I sort of borrowed from C#, although C# definitely did not invent them. Delegates are typed method references. They're bound to a method and its object, so it approximates a closure. So the closure part of it is actually the object that has the state for this function. The syntax in Virgil generalizes the expression.method call syntax of most object-oriented languages these days. It has an anonymous type, so nowhere in there is the actual object type from the delegate mentioned. It's just a function from the argument types to the result type. And because of the syntax, this precludes method overloading. And the reason why that is if we just use expression.method as a delegate, then we don't have any information about what the parameter types are to disambiguate an overloaded method. And in the implementation, this is represented as a tuple. So there are two values there that are bound together in memory. So this doesn't require any memory allocation. So nothing is allocated on the heap when we use delegates, when we pass them around or we take them off objects. This also gives a very efficient dispatch strategy because these two values can be represented as registers locally. And so it's just a couple of register moves in an indirect call. And of course, they're represented as scalars, so any local compiler optimizations can be reused. I'll give you an example code here. So at the top, we've got a list class, and it's got the familiar things. It's got a field that is the head of the list, which is a link. We assume that's the type for every link in the linked list. It's got a method to add an item, and we're assuming here that the item type is the type of the things that we actually put in the list. And then it's got this apply method. And the apply method takes a delegate called f, and it's a function of item, which does not return anything. And the implementation just loops through everything in the links and calls that method with those items. And then the client down at the bottom can actually use that apply method to implement two different things. For example, it can implement the printall method by just passing its own print method to this apply of the list. It can also implement copying of lists by taking the add method of the destination list and passing it to the apply method of the source list. So are there questions about that? Yeah?
So does this give you the ability to do the equivalent of a function pointer table?
It's more powerful because when you have a delegate reference, so the question was, is it equivalent to sort of a function pointer table? It's more powerful because the delegate is actually bound to an object. So when you have a function pointer in C, it's just a pointer to some piece of code, and there's no state associated with it. But in Virgil, when you have a delegate, it's actually bound to an object, so any state that object has is accessible from within the method implementation. Does that answer your question? Okay. So I'm going to talk about raw types real quick. So the real problem that raw types are going after is that this bit twiddling code that you do in low-level drivers is very tedious to write. There's unnaturally sized fields and bit layouts of various hardware registers, and this comes from the hardware guys, so there's really nothing you can do in software to get around that. And masking and shifting of these quantities is very error-prone. You end up with some arcane-looking code, and it may not even be the most efficient code. So really, we'd like to make this we'd like to have a way to express this at the language level that is easier and also perhaps more efficient. So what raw types do is they model bit level values of a fixed width. So any type k in the set 1 through 64 is a k-bit value. So you know exactly how wide a bit type is. And all the bitwise operators that you would normally have on integers are instead defined on these bit types, and they all model the width. So it actually keeps track of how wide these things are, so you don't sort of lose bits without knowing about it. And then the array subscript operator accesses bits of a raw type value like an array. So you can actually access a single bit of one of these values just by indexing by its number. And then all of the literals that you write in your programs are model the width too, which is computed from the width of the literal. So for example, this hexadecimal literal here with 3 hex characters, that's 12 bits. So that actually has the raw type 12. And then the binary one has 5 bits, so that would have raw type 5. And of course you can convert integers and characters and booleans to bits, do stuff, for example, apply these operators on those bits and then convert them back to integers and characters and booleans. But you can't convert references to raw types. Yeah?
Signed and unsigned?
All raw types are unsigned.
And what advantages do these have over bit fields in C?
So you can't have you can't use structs, bit fields, well as values in C. It's sort of unnatural. So all the operators here model the bit width too. So you don't there's sort of this implicit, sort of this guarantee that you don't sort of lose information without knowing about it. Other questions about that? And of course the hardware registers have raw types. So you know that when you're reading a hardware register, you're getting bits and you have to do something to them to get to your higher level program types. Okay. So now I'm going to talk about the initialization phase. So Virgil has no dynamic memory allocation whatsoever. So when a Virgil program is running on a device, a microcontroller, you cannot allocate objects and you cannot allocate arrays. So this actually seems rather draconian, but the people who are developing microcontrollers now are already living with this. So for example, when you program a AVR in C, most people just statically allocate their data with global variables and arrays, and then they manipulate that. So people who are writing at this level are sort of already familiar with that model. What Virgil gives instead of just statically allocating and declaring these arrays is instead the notion of a compile time application constructor. So inside the compiler is actually an interpreter for the entire language, and you can perform any computation whatsoever in that interpreter. So what this gives is the application an opportunity to allocate objects, arrays, initialize them, build an object graph, build data structures, configure itself, test itself inside the compiler. In fact, it's Turing complete computation. When that phase is done, the reachable heap is actually compiled directly into the program binary. And then that heap is available to the program when it's running on the device at runtime. And then further allocation is disallowed. So what this allows is not only for an application to allocate and initialize, configure itself, but also the compiler has the entire heap, so the compiler can do sophisticated space optimizations. So I'll give you an example of initialization time. So on the left, there's a sort of this example program. That is a sort of a sketch of the code of this program. It tells you what the components of the code are, tells you what the entry point, the main entry point is, and also tells you the entry points for the interrupt handlers. Then on the right, we actually have the implementation of this program in terms of code. So we have this strobe component. You can see it has a tree field, which is of type tree, which is allocated to be a tree object. And then inside this constructor code, which is run inside the compiler in the interpreter, it can actually perform any computations. You can call methods on the tree object and add some things to this tree, for example, and then performs some other computation, and then maybe at the end it calls the balance method, which we assume does something to the tree to make it logarithmic in height. And then at runtime, that tree data structure can be reused. So in this timer, we have this interrupt implementation that checks to see whether this number of the count is within the tree, so whether I should actually toggle the LED is if it's a 6 or a 9 or 11 or a 300. So are there questions about that code?
So is it only code that's inside constructors that are interpreted during compile time, or can you have any code that's partially evaluated and whatever?
So the starting point is the constructors, but they can transitively call any code in the program.
Right. Okay, but it doesn't try to translate arbitrary code and see if it can somehow get some
no, at this point, it's not.
Out of it.
At this point, the compiler is not transforming the code; it's just interpreting the code.
Right.
So,
okay.
So it's not partial evaluation; it's actual evaluation.
Right.
Okay, optimization. So there's standard optimizations when you're in this sort of world where you have the whole program and statically compiled. So you can do devirtualization, where you actually resolve virtual method calls. You can do inlining, you can do constant propagation. All of these things are standard techniques that are known, and they're good. I'm not going to talk about them because they're known. I will talk about two optimizations. So I'm just going to mention briefly, which I did before, orphan classes. These require no metadata. So again, if you have a class in Virgil that's not related to any other class, then instances of that class can be represented without an object header. So its type information is known statically to the compiler, so it doesn't have to be on every object. And then reachable members analysis is a way to remove dead code, data, and fields from the program. And reference compression is a way to exploit the the type safety of the program to compress references and therefore save RAM space. So anytime you build a software system, it gets bigger than it should be for any particular use, because drivers and libraries and kernels have general functionality that are, sort of supposed to provide for any client, but a particular client may not use everything in a library, for example. So there's unused states and modes for a driver. There's data structures, methods, and fields that may not be used for a particular program. So an example might be, you have a timer driver, and the timer driver keeps track of time and parts of your program. For example, maybe you want to be notified when a particular time in the future comes. So there is a delta queue inside the timer that people can register callbacks. Well, if your program doesn't actually use that part of the timer, then there's no reason to keep that data structure. You can actually remove that data structure from the program. On a more fine-grained level, you could think about a doubly linked list. You have links forward and backwards through the list, and maybe your program only allocates and initializes doubly linked lists and only goes through them in the forward direction. Then if you never actually need the backward links, you should be able to remove them automatically from these objects. And because RAM is so precious on a microcontroller unit, we want to do this automatically in the compiler for every application. So the goal is to only include the used code and data, the reachable code. And then we can remove all the dead code and all the dead fields and all the dead objects from the program and minimize its overall footprint. So, traditional approach to this problem is that we explore some kind of call graph. We start at some entry point methods, and we transitively include the called methods by looking at method dispatches in the actual code of the methods that are live. So after that is done, we've got a set of live methods that we consider to be live that can be executed at runtime. And then we would find the live fields by analyzing this code and just looking at field reads and writes. And then after that, the complement is the dead fields, and you just take those dead fields away from the objects in the heap. So this requires some kind of call side approximation. So there are a couple of analyses to do this: class hierarchy analysis, rapid type analysis, and flow analysis. But the thing about this is that these optimizations were designed in a world where they didn't have the entire heap. They're static optimizations for programs that dynamically allocate, and they don't leverage heap-specific optimizations or information. So this gives rise to a problem which I call a liveness cycle, which I'm going to illustrate. So we've got another example program here. So we've got a main component. It's got three fields, F, G, and H. They're all of static type A. And when this code runs in the initializer, they're each going to be pointing to three different objects, which are these objects here, A1, B1, C1. And they're an A, a B, and a C, respectively. And then the entry point method has this loop, which calls the M method of this A class here on the F field. And that's supposed to return another A. And then it just assigns that to F. You can sort of think of this as like a continuation-based interpreter, right? You call an instruction, and the instruction tells you what you should do next. So it's a very simple loop here. If we sort of analyze this at our sort of human level of intelligence, what does this program do? Well, we know that from the initializer that this F field points to an A object. It's an object of exact type A. It points to this A1 object. When we call that method M on this A1 object, we get this implementation. So this implementation doesn't do any work. Maybe it does some work that doesn't access any fields, and then it returns itself. So when this method returns, it actually gets the same value, the same F value. So this whole loop can basically be turned into a no-op, or a loop over a no-op, plus whatever computation might be in that A method. So are there any questions about what that program does? Okay. So how does reachable members analysis work? Reachable members analysis is sort of a way that we can teach a compiler to do the same thing we just sort of did with our minds and get the same result, get the same precision, hopefully. So what we're given is a entry point methods and a live heap. We're going to assume that everything is dead until it's used. And then when we need to approximate a method dispatch, the call graph approximation is going to use live objects only. So everything is dead, and then when an object becomes live, then it becomes considered for a virtual dispatch in a program. We can assume that there's no dynamic memory allocation in the case of Virgil, but if we want to generalize this optimization, we can conservatively include the allocation sites too. So this turns out that it's more precise than class hierarchy analysis or rapid type analysis. The reason why that is because the objects and types are considered on demand and avoids this liveness cycle. Okay. RMA uses a queue of things, and the things can be method implementations, they can be heap objects, they can be types, they can be fields and methods, declared fields and declared methods. So I'm going to represent that queue just with green arrows. So it turns out not really to matter what order you process the green arrows. So we don't really have to keep track of the order here. So I'm just going to use the green arrows. So we're going to start at the entry point methods and assume that everything is dead until it becomes reachable. Okay, so we're going to start over here in the heap with this actual live object. Remember, it was considered live because it's sort of the entry point, of the program. So there's nothing there live, and we haven't analyzed any code yet, so there's nothing to do. Now we're going to analyze this method implementation. And the things that we're going to look for are field uses and method calls. So we're going to analyze this code and see that it actually uses this field main.f. So we're going to put that field, the declared field, in the queue. We're going to continue to analyze that code and see that there's a method dispatch, a use of a.m. So we're going to put that declared method in the queue. Not a method implementation, just a declared method. Think of it just the name of the method. Okay, there are no more field usages or method calls in that code, so we can move on. We're done. Now, we're going to analyze this declared field. And the way we're going to do that is we're going to look at all objects of this type in the live heap so far. Because this is a component, there's only one object of that type. And we're going to analyze that field of that object, which is that field over there. So we're going to put that in the queue. That live field of that live object in the queue. Okay, and now we're done with that because there are no more instances of that type. We're going to move on. So now we're going to process this declared method. And again, when we have a field use or a method use, we're going to look at all live objects in the heap so far and analyze their version of that field or method. And there aren't any live objects of type A in the heap yet. So we're done. We can move on. So now we're going to analyze this live field of this live object. And it points to this A1 object. So because we saw a field read of this type at some point, we're going to pull in that actual object and put that in the queue. So we're going to analyze this A1 object later. Okay, so that's the only thing that field points to. So we're going to pull that in, put that in the queue. So now we're going to analyze this A1 object, which is of exact type A. And we're going to look at its declaration in the left side of the program and see that method M is actually used in that type. So we have we know that if we were to actually dispatch on this actual object, we would get this method implementation. And because of that, we're going to put that in the queue. So now we're done with that object, because that's the only member that's live of its type. So now we're going to move on and analyze that code. And there aren't any field reads or method calls in there, so we're actually done. And this is a slice of the program that we would get if we were to run RMA, which is, I claim, well, at least for this simple program, it's the optimal slice of the program. So what would happen if you run class hierarchy analysis? And I claim that you'd get this. And the reason why that is that virtual dispatch right there. So we can look at field F and its declaration is static type A. And the way class hierarchy analysis works is you start with that type, the static type of the object reference there, and you look at all method implementations below it, which would be these three method implementations. And because this method implementation uses G, which is that field there, then that B object has to be live. Okay? And because it uses, because this method implementation is live, then that field Z is live there. So there's sort of a cycle here, where if you use this G field, it points to a B object. Okay? And the B object has a method implementation which uses G. So there's sort of this cycle between these usages in the program. So anytime you analyze one of them, you'll get all of them. Other questions about that? So what if you use rapid type analysis? So you actually get the same slice of the program. So rapid type analysis uses an approximation of the heap. Again, because it was designed not to work with an entire heap. So it just has a set of live types. And because we've already run the code in the initializer and allocated objects of type A, B, and C, it would have to start with that assumption when it analyzes the code. So when RTA analyzes that same virtual dispatch, it will get the same three method implementations, and therefore it will have these same objects reachable in the heap. However, now because this C1 object is not reachable, we can actually run RTA again with a better approximation of the live types. So if you run RTA with a better approximation, you actually get a smaller slice, but you don't get the same slice as RMA. That's because we had this liveness cycle where you have this method implementation, this method dispatch here. This field is live, which points to a B, which has a method implementation that points to G. So we still have the same liveness cycle. So you can't actually...
Could you go back and explain the RMA result a bit more? So one question I have for you. Okay, so in this case, you're actually starting from the entry points. You mentioned in the RTA example that you had to run the static initializer. So the question is, what happened to the static initializer on this one? Why didn't you have to run it?
Oh, we did run it. We already had... RMA does use the result from the static initializers. It has the entirety.
What you're saying is you end up with having objects A, B, and C on the heap.
Yeah.
Okay, because that wasn't shown in this picture. You have A, B, and C on the heap. And then when you do your RMA, you actually determine that you only need A, and B and C can be thrown away. Those instances of B and C can actually be thrown away. Okay.
So normally RTA and CHA operate in an environment where you don't have any heap whatsoever.
Yeah.
So you would...
Based approximation of the... Okay.
Okay. Other questions about why that would happen? So you can actually show that, you could actually run maybe another iteration of RTA. So in fact, you can iterate RTA to a fixed point. And if you do that, this is the fixed point you would get. And it is slightly larger than the slice you would get with RMA. So there are other questions about either RMA, RTA, CHA, why that shows up. Okay. Reference compression. So reference compression is an optimization to compress the heap as opposed to removing dead things. So normally, pointers are represented as 16-bit integers on an architecture that has less than 64 kilobytes of memory. So that happens in C because you can do pointer arithmetic and basically generate any byte address by doing pointer arithmetic. And the semantics of C is sort of, well, not that there really are semantics of C, but the semantics of C sort of, there's this built-in assumption that you can do this arithmetic. But actually, in a language that has static type safety, the types restrict the set of things that you can reference with a particular reference. So if you have a reference of declared type A, it can only point to A objects or one of A's subtypes. And because we have the complete heap available after the initialization code runs, we can use this to represent the references in a special way to compress them. So there's actually extremely simple way to do this. Just use a compression table. So instead of using pointers directly to memory, we can just use an object handled table. So that the handle of an object is just an index into this table. And then the handle table can be stored in ROM because the actual addresses of the objects don't change because there's no garbage collector, there's no moving. So this trades a little bit of ROM space for RAM space because wherever a reference shows up in the heap now can be compressed down to a few bits. Okay, so give me an illustration of that. Suppose that we have this inheritance hierarchy here, and normally you would have some object class that is at the top of the root, that is the root of all of these inheritance trees. We don't have that in Virgil, so we can get rid of it. So we can actually consider all of these class hierarchies independently, because you can't have a reference, for example, a reference of type A that could ever point to an X object or an M object, and vice versa. So if we look at these triangles, sort of give you an illustration of the referenceable set. So the referenceable set for A is actually anything that's in this subtriangle. An A reference can point to an A, a B, a C, a D, or an E. And similarly, B can only point to things that are below it in its referenceable set in this triangle here. We can just do a very simple approximation and merge all of the triangles together. Now again, if we had object, these would all merge together into a single triangle, and then we really wouldn't get anywhere. But now what we can do, we can simply just count the number of the live objects in the program heap because it's all been allocated in the compiler. So for example, maybe there's only 15 objects of any type in this left tree here. Maybe there's only one object in the center. Maybe that's like sort of a configuration class or something like that. And maybe there's lots more of this other guy over here. And then what we can do, we just simply introduce a ROM table, a handle table that's stored in ROM. So any reference is represented as an index into one of these tables, and the actual size of the reference is the logarithm of the size of the table. And then those store the actual RAM addresses of the objects. And then any object operation you do, like reading a field, you just first go to the table, get the actual RAM address, and then you can do the object operation. So, yeah.
Is it worth doing, how much can you trade performance as in CPU time for memory? Because you could imagine you allocated all the objects in the A hierarchy consecutively, and then you just gave, here's the pointer, and then there's a sequence of deltas.
Right. So I don't have performance numbers in this talk. I actually finished them this week, and we submitted another paper about the trade-offs between execution time. And it turns out to be between 50% slower and 100% slower to do the reference table approach. But the good news is that we have a new technique that has essentially zero overhead for doing compression of pointers. And I can tell you about that later, but I'd have to kill you. No, I'll tell you about it later. Okay, so we did some experiments. We did 5 demo very simple applications. So the reason why that is one, so this blink program just flips the LEDs on and off periodically. So there's a timer driver that is implemented, and then the timer goes off, and then it actually flips a pin on one of the microcontroller package. That's not really to demonstrate that Virgil is fantastic for kicking the crap out of small programs. That's really just to show that if we have a small program, we get a very small binary and a small heap. So sort of measuring the fixed cost of Virgil. Count LEDs is just a little bit more complicated version of that. Uses a couple more objects there. List is just a simple benchmark program that manipulates some linked lists. Decoder is actually a fairly complicated program. So what a decoder is basically a bit pattern recognizer. So you can think about building a bit pattern recognizer for machine instructions. So there's a window of bits that correspond to a particular field, right? And if the field if those bits have a particular pattern, then you look at another field of bits, and then you sort of have this decision tree. So what the decoder is actually a library for doing this very, very simply. A decoder library actually takes bit patterns as input and produces a disambiguation tree, the optimal disambiguation tree. And what happens in this application is that in the initialization phase, because you can do any computation, what the application does is it feeds all the bit patterns to this library. And the library generates this data structure, which is a tree, a disambiguation tree. And then the tree itself is actually saved, and then all the library is not used at runtime. So all it does is build this as this complicated algorithm for generating a disambiguation tree. And then MPK is actually a part of a operating system kernel, the SOS kernel, which is developed at UCLA. That was ported to Virgil by Simon Hahn. It's basically, it has modules and it has messages, and each of them are represented by separate inheritance hierarchies, and then there's double dispatch between them. Okay, these all share common device drivers. Excuse me. The general purpose I/O ports and also the timer. There's no native code here. All the drivers that are needed to run on the bare device are actually implemented in Virgil, and they're included here in all of the results. So this is just to give you an idea of what the fixed cost is, the baseline compilation. So the Virgil compiler generates C code, and then I use GCC to generate machine code for the AVR architecture. So the first column is a code space, and the first number in that column is GCC with no optimizations, and then the second number in that column is with GCC O2. And that's just to sort of give you an idea of how well GCC does in terms of code space. So you can see that all the applications after optimization fit in less than 3 kilobytes of code. And in fact, this list program actually fits in 600 bytes of code. So the fixed cost of Virgil is actually extremely small. We can write really small programs and not have this big runtime system. And then the RAM overhead, you can see. ROM, that is actually data structures that are stored in ROM. So all of the meta objects and dispatch tables are there in ROM and not in RAM. And then the RAM is for the actual heap. So you can see that all these programs can fit in less than 350 bytes of memory. Okay, so what happens when you actually do some of the optimizations here? So this this code reduction is for performing the RMA, dead code elimination optimization. So there are 5 benchmarks, and then there are 8 bars for each benchmark. This group of 4 bars, which is sort of a bluish, maybe slightly purple color, that is without any Virgil-specific optimizations. And then each of those 4 bars within that group are GCC optimization levels. So this group here is no Virgil optimizations, and then GCC optimizations 01, 02, OS. And then the group of 4 bars above that are when you apply RMA on top of that. And then it's RMA plus a GCC optimization level. So the thing to see here really is this guy here. So I told you about this program and how it works. It has this complicated library to build these data structures. But none of that stuff is really reachable at runtime, because only the result of that is really important. So you get significant reductions. So from 3 kilobytes for an optimized program here down to some 500 bytes. You know, it's like basically saving 80%, or close there, close to 80%. And really, that's because GCC can't do dead code elimination through pointers and through dispatch tables and things. And then there is a reduction for every other program too, and basically removing initializers too. It's like maybe 20 to 30% average for these guys, and then the big story is there. Okay, what about RAM reduction? Yeah, you have a question? Oh. So RAM reduction. So I'm just going to show 2 benchmarks here. So there's 3 bars each. So the baseline is with no Virgil-specific optimizations. And then the bar above that is with RMA, which is the dead code dead data elimination. And then the next bar above that is dead code dead data elimination plus reference compression. And each bar is broken up into categories. So the blue category there, that's primitives. That's integers, characters, booleans, arrays of those things. Those are not compressed. Okay. And then the next category is references, which are object references and delegates. Those are compressed by reference compression. And then the last bit there is metadata, which is like things like object headers, array length fields, and such. And then alignment, which is the last gray bar, those are bits that are left over at the end of objects after we've compressed references. So you can see that after we do dead code and data elimination, we can get rid of all categories of data. And then after we do reference compression, we can actually get a total savings of about 41% on the RAM. And that was more typical of the benchmarks. This one is not typical, but I just wanted to show you how much of a difference it makes for getting the fixed cost down. So you start with a base of some 50 bytes of memory, and then after dead coded and data, you get down to some 14 bytes of memory or something like that, and then there's not really much left over to compress. Okay, so there's a trade-off between RAM and ROM, at least for the compression table approach. So this is a comparison of RAM and ROM. So there are two groups of 3 bars. So the bluish bars there, that's RAM, and then the red, orange, and yellow, those are ROM numbers. Okay, and then within those groups, the baseline is no Virgil specific optimizations, then again, RMA, which is the dead code, dead data, and then compression. So you can see that when we apply RMA, we remove all categories of data. Okay, so even ROM goes down. And then when we apply reference compression, we trade a little bit of ROM space for RAM. And generally we don't add very much ROM at all. And ROM is generally 8 to maybe 16 times larger. So it's not a big loss to trade ROM for RAM. Are there questions about that graph or previous graphs? Okay. So the conclusion, at least my conclusion, I don't know what your conclusion is that objects can fit in the space gap. And I think the Virgil solutions draw on some language design for lightweight features and still getting the bang of object-oriented programming. A new compilation model where you actually allocate objects and initialize them inside the compiler. Having a minimal language runtime, which basically boils down to getting rid of features that require a runtime. And then also doing aggressive compiler optimizations that were not possible without the new compilation model. So I demonstrated some practical results. All these applications run in a hardware simulator, and we've run them all on the hardware too. So these are actual programs. These aren't made up. And we did get some real resource reduction from these optimizations. So some current and future work. So I worked with David Bacon at IBM for a summer and a little bit after, and we applied these ideas to Java. So reusing the idea of initialization time to initialize not only the program but also the virtual machine, and then to do program slicing not only over the program but also over the virtual machine itself too. So we have a paper in PLDI 2007, if you want to look for it. It's called the XOVM. So I have released the code of Virgil, total source release, so it's under the BSD license. That's the second release. The first release was in January, and I hope to have another one within the next couple of weeks. So there's always more work to do on language and runtime features. So parametric types, I'm sort of in beta now. They work in the interpreter, but not very well they don't work in the code generator. And those are really necessary to do the types of extensibility that you would normally do in Java with some Java-Lang object type. So there's not really much of a module system or dynamic loading. In fact, there's no dynamic loading. But I think the two concepts are really related. I think you need a module system to be able to reason about what parts of the program can you dynamically load. So, because we're doing these whole program optimizations, what I think needs to happen, there needs to be a module system that you can sort of wrap up a piece of code so that you can optimize within the module. There's no support for direct memory access. That's important on some microcontrollers. And there's no dynamic memory allocation. There might be ways that you could hybridize Virgil where you have maybe some region-based allocation, or maybe you have reference-counted primitive arrays or something like that. Or maybe, even on a larger device, a general-purpose garbage collector. And of course, there's always work to do on tools and development tools, debugging tools, testing tools. And there's always code to be written. So we have some undergraduates that are cranking out Virgil code, writing drivers for AVR and writing applications and starting to build sort of a low-level operating system service layer. So thanks for your time. I'll answer any questions.
I have a question. Have you looked at all at code compression?
So I haven't done any work on code compression, but there are definitely people at UCLA that I've talked to about code compression. So again, it's a trade-off between. So the the reference compression is a trade-off. So we didn't have numbers for how much reference compression increases the code because it wasn't fully implemented at that time. But now we do, and it's like you trade about 20% code space. So code gets bigger because of reference compression because you have extra indirection. Maybe you could apply code compression on top of that to get the code space back. So yeah, there are definitely ways. There's definitely, the compiler needs to trade off all those dimensions.
Assuming that the RAM is the biggest constraint, most constrained resource. I had one other question, which was related to libraries. So it seems like unless the library is specifically written for it, that it could end up pulling in just incidentally pulling in a lot of stuff from the library that's not particularly important just because it's referenced by the stuff that is used. And so do you have to pay special attention when writing Virgil libraries to sort of keeping things decoupled and prevent a lot of
That's a pretty good question. So his question was basically, do you have to pay special attention when you're writing a library to keep things decoupled so they'll be sliced apart? And well, we don't have enough experience writing enough code to know, but I think that this optimization will be good enough to cut away most of the cruft that you get from a library, because it actually does an approximation of what could be invoked, and it is based on actual live objects. So I have hope that this optimization will help stave off that sort of feature bloat of libraries. Yeah.
Yeah, so it seemed like there were two separate parts. There was the new language, and then you had some optimizations. And of course, because the language had its own restrictions, then it was maybe easier to work on those optimizations. But it seems like a lot of those would be applicable without the language. And I guess you mentioned that you tried at least one of them with Java, but something like having noticing feeds that are not used would simply be something you could add to GCC as well, or anywhere, and that would be useful. I mean, so did you kind of evaluate on how much depended on the language and what?
Yeah, so sort of the key part that makes the reachability sort of work in the way it does is the availability of the heap. So if you think about maybe doing this optimization in a virtual machine as it's running, where you do have the heap, that might be interesting. I've sort of thought about that in the background. I haven't done any actual work on that. So I didn't give you a whole lot of detail about what I did at IBM, but really what we did was so we wanted to take the same virtual machine and reuse it for an embedded system and reduce its footprint. And we're willing to make trade-offs in terms of what applications we would support. So the way we did it is basically you load the Java program into the Java virtual machine. And the Java virtual machine is implemented in C and C++ and some machine code here and there. And then we initialize the entire virtual machine. That act of loading the program in causes it to initialize itself. And then we further initialize the application classes by running the static initializers. And then we do this reachability, a similar reachability. And we have domain knowledge from the VM implementation that says, if you use this Java thing, then it means this VM thing. And if you use this VM thing, then it means this other VM thing. So there's like a constraint system. And then the program slicing all works on that. But that's all static. But it's sort of the same echo of the same idea. So I think there is more mileage to get from this idea, yeah.
And you might also combine it with some runtime, profile it and see what actually gets used or something like that.
Yeah. There is one sort of thing that gets you is once you have dynamically loaded code, if you're doing dead data elimination, you're removing fields from objects, and then you load some new code that wants to go look at those fields, then you're in a bit of a bind, right? So you have to make some kind of assumption about what the dynamically loaded code can do.
There has been work on Java cards, right? Which seems like a similar situation. There is a ROM, there is a RAM, you have to save. And so can you compare what's happening there?
Well, I think they're probably at least an order of magnitude or 2 orders of magnitude larger footprint than Virgil is targeted at. So the Java card stuff still, if I can remember correctly, you still do static deployment, but there's still this idea of a virtual machine. So there's some virtual machine underneath that is implementing all of the language. And Virgil is designed so that there's sort of nothing underneath you. You have the language, and you have access to the hardware, and really there is no runtime system that's implementing the language. So it is sort of fundamentally a different model than Java, even in the Java card case. Does that answer your question?
The work you did in IBM, that was kind of the larger scale?
That was a larger scale thing where you could think of this program slicing as slicing a program. And then the IBM thing was sort of program slicing with some domain knowledge where the program happens to be a VM with another program inside of it. So is that sort of...
So your ideas could be used for the Java card?
Maybe. I haven't looked into a lot of detail on the Java card, but maybe.
And you don't know if they do it or not?
I don't think that they do anything like this. I mean, they must have something to remove dead code, but I don't think it's this sophisticated.
So how does the embedded community in general take to this approach? I mean, what's the size of the corresponding C programs for doing blinking LEDs and all this stuff? Have you gotten any feedback in that direction? Do they say, okay, well, this looks nice, it's nice and object-oriented, it's type-safe, but it's using twice as much memory and we don't really care about you? Or is it, well, this looks cool, we get all this type safety but no extra overhead, we should buy into it?
Yeah, there hasn't been enough comparison with actual C programs that are implemented, by hand to do this kind of thing. So I haven't yet won over those people. So I don't know if that answers your question.
You have to try it.
Yeah, they're mostly have not presented this to embedded systems people, just because of my area as programming languages. But yeah, there are people that are aware of it. There are people at UCLA, for example, that developed SOS that are very interested in getting sort of Virgil modules into their operating system or comparing a Virgil-like or an operating system like theirs implemented in Virgil to theirs. So there's interest there, but those comparisons haven't been made directly.
But have you compared a C version for that blinking LED stuff with the output of your compiler?
My guess is that it would be. So what was our code size on that one? Let's see. Yeah, 704 bytes of code and 50 bytes of RAM. I think it's 14 bytes of RAM after optimized. My guess is that a C program would be, would not be a factor of 2 smaller. So this would be, I think this, at least for Blink, it would be within a factor of 2. But that's just a guess, just from my experience. Because the actual C program that comes out of my compiler has almost nothing in it, right? Yeah.
So do you care to speculate, what would it take to convince the embedded people, and how? I know you're the language person in your team, or one of them, but what should the team as a whole do to actually engage the embedded controller people and try to actually get this deployed?
That's definitely a tough question. I think our strategy right now is that we need to build code that people are going to use, and that will convince them. When our code written in Virgil has so much easier to use, but is implementable as efficiently or close enough that it doesn't even matter, then they will be convinced. Because I don't think that you'll necessarily say, okay, look at our language, now rewrite all of your stuff in our language, and then you'll be convinced. We have to convince them by actually building a system in this language and showing that it can do what they want to do. So what we're doing is sort of building bottom up. We built device drivers now, so we have device drivers for most of the AVR. And in the next release, I want to sort of release here's an AVR kit that you can write Virgil programs with and play with it. And then the release after that would be, here's some things that another layer that we built on top of it in Virgil. So it's sort of climbing the abstraction layer. And then I think when we have a complicated enough system, I think that will be more convincing. So that answer your question?
So there's been some significant work in sensor networks, which seem to fall somewhere between the Java card and your system in terms of resources, with the provision that if you run out of power, your sensor is dead. So have you thought about how your work might relate to what people are doing with programming?
Yeah, so I have a lot of contact with those people. So I know most of them, firsthand, are all my friends and everything. So the way it breaks down in sensor networks, it seems like there's almost a bifurcation. There's two worlds. So I did all of my work actually targeting the sensor node that they're writing their operating systems for. So it's directly comparable to them. So they're directly interested in that. And then the tier above that is like the Stargates where they're running Linux. So sort of always in the back of our mind has been that this will be applied to sensor network stuff. So one of the things that we're doing is now that we've got all of the AVR drivers, we're building the driver. If you look at the very first slide, so this sensor node there, we built pretty much all the drivers for the on-CPU things there. And now we're building drivers for the off-CPU things there. So we're building a driver for the radio. So we will soon be able to speak their language and have our node speak their protocols and then basically participate in the sensor network on the actual, on the packet level, essentially. So yeah, it's something that we're definitely interested in getting our stuff applied there. Yeah.
Question about, so in cases where you're performing an operation that could be implemented in different ways with different size speed trade-offs, can you use the state of the heap to make implementation selection decisions?
Can you make implementation decisions based on the state of the heap or the shape of the heaper? That's something we definitely thought about that, and we want to explore that. So we have this new paper where we do compression in a different way, and it turns out that the compression isn't as tight as if you did the table-based compression, but it runs faster, and maybe uses a little bit less code space. So there's a trade-off there, right? Not as good compression, but faster, right? And then of course there's the totally big case where you're not compressed and you run the fastest. And one thing that we wanted to look at is to automatically trade off between these. So maybe you compress the part of the heap that is not used very often at all, with the highest compression but slowest. And then the part that's used the most often, maybe you don't compress that at all. And then maybe something in the middle, you use the in the middle. So now we have several, sorry? Yeah. So now we sort of have several different implementations, and now the question is whether we can automatically trade off between those.
I don't think, it's maybe at the second slide or something, that you have something where you say you really worry about memory and you worry about energy. Have you done anything about the energy part at all?
No, we haven't done any work on energy consumption. And at least as far as microcontrollers go, basically instruction selection doesn't mean anything. So people have done work and just measured the consumption. Does it vary from instruction type to instruction type? And the answer is no. So what really matters is performance and also sleeping. And sleep states, that's operating system level decisions. And for performance, that's just raw compiler optimizations. So.
But that means, for example, if you don't do compression and get higher performance, you may actually have less energy consumption.
Yeah. So there have been people who, for example, write applications in a much higher level language where they just talk about tasks and things like that, where the scheduling of tasks is not built into the language. And then they have some, basically, I wouldn't necessarily call them compilers, but compilers that translate that into task-oriented code that optimizes the energy consumption of this set of tasks. But that's sort of at a higher level than what this is targeted.
What happens if a program fails a runtime check and null pointer check?
So currently what happens is it will terminate the program, set a little piece of state in the registers that will tell you the code, and then in the simulator it will give you a stack trace. So if you run your code in the simulator, you get stack traces at the source level. If you run them on the device will reset or just, basically halt. So, yeah. So there's not really a well-developed exception model in Virgil. So you can't throw exceptions, catch them, and walk stacks and things like that. But
so have you thought about, from your work, what might carry over to a more general purpose environment, sort of, a PC environment, or, obviously there's work you did with David Bacon at IBM, but are there other things from your work that you think would carry over? What would you add if we were to say, here's C# and extended to better support programming? What kinds of things would you add based on your work here?
Well, the first thing, this is sort of simple, I would add raw types to C#. I would add bit level types and all the bit manipulation stuff to C#. That's one thing, but that's sort of a small thing. I think in terms of sort of program analysis, language infrastructure, I had this idea that, so what we did with the XOVM was so tough because of just the language implementation, the implementation language of the actual virtual machine. It's all written in C, all written in C++ and machine code. So what we wanted to do with the virtual machine, we could not really automate. But if you had a language infrastructure that was implemented in itself for metacircular, maybe you could do metacircular program analysis. That's something that really interests me, is whether you could analyze the implementation of the virtual machine and do all of these cool stuff, not only to the program, but also the virtual machine that it's in. And I get the feeling that if I had the kind of analysis that at least I can imagine, we could have done the XOVM in 2 weeks as opposed to 7 months. And I think that would be really a big advancement in the state of the art.
One other thing, though, so if I'm an operating systems programmer, what might I want from your system that you would add to C#?
Can I add things that are not in my system to C#? Sure. Okay. One thing is that I wanted to add this, but sort of not gotten to, is the way to actually describe the layout of data structures in memory when it matters. So, for example, packet format, the format of a device driver block of memory where you interact with the registers of a device driver. That's something that I think is absolutely necessary at the operating system level, which is not in languages that give you the abstraction where you've got classes and objects, but you don't have any control of the layout. I think it's good that you don't have any control over the object layout, but sometimes it really, really matters. And if you had sort of a way to say, yes, I really mean this layout, in a way that is set off, and then the compiler implemented that, so you didn't have to worry about, doing that manually. That would be really useful, I think, to operating systems people.
How about the static class or static class initialization? You've basically done something that people usually don't do because they say, well, I don't know if the compiler will terminate, and I don't want to run a Turing machine interpreter inside my system. Would that be something that you think would be useful?
Oh yeah, I think as a programming model, I wish that I had initialization time in Java so that I could write my programs so that they compile, so they allocated stuff in the compiler, and it was just there when you start up. I think that would really simplify, it could really simplify the startup of many different systems, especially complicated software systems, operating system kernels. So operating system kernel has to bootstrap itself, right? And it has all this problem. It has no resources. It has no state that's been initialized, right? So it has to. But if you could sort of bootstrap it in the compiler and have stuff ready to go, I think that'd be useful too. Yeah.
So my question was actually kind of the opposite. That I'm thinking, like, if you have this kind of better macro facility, essentially, where you can run code at compile time, so why then go with the limitations you have of the embedded language, and why not have something big more, where I could actually have regex and DOM and all kinds of whatever, like you could, like the sky is the limit, kind of.
Yeah.
Right.
So there definitely has been work on sort of like meta-ML, which are these meta languages where you can do computation and process your program in the compiler at compilation time. I didn't want to go into the meta level just because I don't know whether those research ideas are hashed out very well. It's definitely something that could be explored. But I wanted to sort of make the model simple, and the language is the same whether you're in the compiler or whether you're on the embedded device. Does that sort of answer your question?
Sure.
But yeah, I mean, meta languages are really cool to think about and really useful for some things. I don't know whether the models have stabilized, the research has stabilized to the point where you want to camp on a particular idea. Yeah.
Well, I guess your answer is exactly that you need to have some standard of what it is. So it's easier to standardize one language than two. Right.
Yeah.
So I was just thinking that when you're compiling the program, and since there's no dynamic memory allocation, the amount of RAM that it uses is fixed, right?
Right.
So considering that they have a fixed amount of RAM and they're running dedicated programs, any RAM that's left over is just unused, right?
Well, you still need dynamic RAM for the stack. But other than that, up to a point, the stack probably has a maximum bound.
So,
yeah,
so is there any plan to make any use of that extra memory that's left over?
So that sort of goes back to your question about trade-offs. So if you know statically that you have 4 kilobytes of RAM, your program uses 2 kilobytes, but you could use another kilobyte of RAM and make it 20% faster. It would be really cool if you could make the compiler say, okay, I've got the RAM, I will spend it on performance, as opposed to the opposite where I don't have the RAM, I will trade performance to get the RAM back. Yeah. So I think that's sort of the same resource trade-off question. But yeah, that's definitely a good idea. Well, the other thing is, though, the other part of that answer is that so I've learned recently a little bit more about how the business of microcontroller works. If you can save, RAM is energy a lot, and RAM is money. And if you, for example, if you have a fixed program and you can save 20...
Just for smaller RAMs then.
Yeah. If you can save 20% of RAM, you can make a specialized ASIC that has 20% less RAM, and therefore uses, whatever, K% less die space, and therefore costs, 5 cents cheaper. And if you have 100 million of them, that's real money. So yeah, there are different directions. Some people would say just compress the hell out of it and give me the best RAM that you can get, and other people would say, it has to be as fast as possible. It's a question of which dimension is fixed, right? If the RAM size is fixed, then utilize it. If the RAM size isn't fixed, then reduce it.